So yeah, once again, thank you everyone for coming. Our speaker today is Jason Mancuso. We are presenting this talk through Denver Machine Learning Study Group. So if you're interested in machine learning, deep learning, reinforcement learning of any variety, come talk to me afterwards and I'll add you to our Slack if you're not there yet. The talk today will be about OpenMined, and I'll pass it on to Jason, who's the co-contributor of the project.
Cool. So I'm going to first share my screen to YouTube so that people know what's going on there, and then we'll get started with the talk, and then there will be a demo at the end with time for questions in between those two. One sec. All right, so we're here to talk about OpenMined. Let's talk about what that is. OpenMined is an open source community focused on researching and improving tools for secure, privacy-preserving, and value-aligned artificial intelligence. Some of the things that we do, we raise awareness around these three topics, build tools to lower the barrier to entry, and then we have fun hackathons. We have a community. It's a Slack community, about 2,000 people strong, with around 145 contributors to the actual tools themselves. So the outline of this talk, what I'm going to talk about today, I'm going to talk about why the current AI business model has problems, especially related to privacy. And then I'm going to talk about the core technologies that we're developing at OpenMined to help change this, this scenario that we're in right now. And the key technologies that we're going to talk about are federated learning, homomorphic encryption, and multi-party computation, as well as what we call a gradient marketplace. And then I'll finish with kind of the future roadmap of the project and show, hopefully, a demo that I've put together. Jane and Jack's data inside of AI Inc. Maybe it has some personal statistics like demographics information, as well as, in this case, a person's credit history. We're supposing that AI Inc. is doing machine learning on banking information. And then how we generally do this is we train a model that transforms those some of the data into new data. So here we're using personal statistics and demographics to predict something like credit history. We have this data about these people where we have this credit history label, we have the personal stats as our inputs, and we train this credit rating model so that when we meet a new person, Bob, we're able to predict on that person who isn't willing or able to reveal their credit history. This is generally how it goes in the current AI business model. That's how we train models. And then next thing we do is we sell the use of that model. AI Inc. has trained this model that predicts credit history from these personal stats. They go to this big bank where they have these personal stats, but not everyone's credit history. Or if they have it, it's incomplete and they want to fill it in or something. And the idea is that we, as the model makers, then sell the use of our model to these companies through APIs or potentially even selling them the model itself. And then they can use that model in their business. So again, to reiterate, step one is acquire data about people. Step two is train a model that predicts unknown facts using known facts. And then step three is sell the use of that model, which is the app. So some problems with that is that, the first thing we have is we have to acquire data about people. There's a few problems with that, right? As we know, privacy, people lose control of their data. That's a huge problem. Once you send a copy of your data somewhere, your future privacy is at the mercy of whoever you shared it with. You know, and these people you're sharing it with, their revenue is tied to their ability to monetize that data. So their incentives here are not necessarily to do things that are going to preserve your privacy or to help you necessarily. They're going to monetize that data however they can. This is how AI is done generally in the business, throughout the industry right now, right? And so I guess the reason that we do this is because we use apps that collect this data, and those apps or products, services are not available to us unless we give up our data. And for right now, there's we don't have a way around that currently. The next problem is that there are things that don't get made because there's some data that's too private to share. You can think of like HIPAA regulations as a regulatory setup that prevents certain data from getting shared, certain models from being made. But maybe those products, if that data could be shared, would be useful for a lot of people. Specifically things around medical history, medical information, things like psychotherapy notes. If you want to predict a person's, capability of being treated by a certain drug based on their psychotherapy notes or something like that. Those are very private. No one trains models on those, as far as I know. But that's something that could be useful, predicting mental disorders before you have like a psychotic break or something like that. And that's impossible to do given this current AI business model. The other problem here is that we're training a model that predicts unknown facts about a person using known facts. That means that we have this contagious privacy loss. If a certain subset of people give up their data to allow this model to be trained, it's possible that this model can then be used to predict private information about people who did not give up that information. And here we're specifically talking about the labels, right? If some people give up those labels, some people don't. But if you can access the features that are used to predict those labels, and you have a well-trained model, you can predict or infer those labels about people who didn't give it up, which is a problem because it's kind of like a race to the bottom as far as giving up your privacy goes. And then the other problem with this is that there's lack of competition. There's very little market competition because these data sets become proprietary and they get centralized in these silos within corporations. Sometimes there are multiple silos within a corporation, right? Some teams can't get access to some data while other teams can. And again, that's another reason for this being a problem as far as innovation in AI goes. This privacy problem is preventing innovation, not stimulating it. So the last thing then is unfair predictions here. The data that we're training on, it being centralized by one corporation and being gathered through one or a few services means that that data represents a specific population, the users of that service. But maybe the model is going to then be applied to people who don't use that service, and that means that we're applying to this model to a distribution that's fundamentally perhaps different than the distribution of the data that we trained on. If you've trained a model like this, you know that this is essentially something like overfitting. And this data being siloed leads to this overfitting. The main problem with being we don't have a test set until we apply it on the real world. And at that point, it's too late to prevent it, right? We've already unleashed it on people. It's already affected people's lives, unfairly perhaps. So that's a problem with the current business model. And then finally, we're going to sell the use of that app. That was the third problem. One problem with this is there's lost natural income. People give up their data and help build these models, but they're not being compensated for it. Yeah, I get to use Facebook, right? But all of the models that are used with my Facebook data, they would not exist without me or people like me contributing data to them. That's economically speaking, that's kind of like almost labor exploitation in a sense. This is information about me that I could be using to transact with in a marketplace and benefiting from, because it should be, in theory, my property. So another problem is that we don't know how valuable that data is. Even if I could transact with my data in a marketplace, right now we don't have any way of determining how valuable my data point is to that model, and in turn, how do we price that data in a transaction? And then again, here we don't know how accurate the predictions are until we've deployed the model. And this comes up in step 3 when we saw the use of that model without this data being desiloed in a sense, and us being able to train on accurate distributions or accurate populations. We don't know the quality of the deployed model, and it's likely that we could overfit. And then finally, these models are digital assets and they're hard to protect. If we're going to send models around, it's kind of important that people not be able to sell those models to the next corporation. If I'm Google and I train a model and I send that model down to your phone to help improve it or whatever, if someone copies it and tries to sell it to someone, that could potentially be a loss of a few $1 million to Google in theory. So obviously we want to prevent that when we're actually embedding these models in applications. So that's a lot of problems with the current AI business model, which is funny because if you read the popular articles on this subject, it seems like AI is doing really well and doing a lot of good things for a lot of good people. And I think that's true, but we just still need to fix these things, right? So we think we have a potential solution. Otherwise, it wouldn't be, I wouldn't have finished all of the problems in 15 minutes or whatever. But so one potential solution for the privacy stuff is to train AIs on data that the AIs can't see. So obviously we get this privacy win here. People wouldn't need to reveal their data, and so in theory, the centralization of data doesn't need to happen, which means that that data is less susceptible to being stolen by hackers potentially, or the company itself can't then use that data in potentially malicious ways. So if we can train models on data without revealing the actual values of the data, we have a privacy win. Maybe it won't solve the problem completely, but it'll get us closer. So again, to remind us of the outline of this talk, we just covered why this AI business model and how it has privacy problems. And now I'm going to start with an introduction to the core technologies of OpenMined. Start with federated learning, go through homomorphic encryption, multi-party computation, the gradient marketplace, and then we'll get to roadmap and demos. First, federated learning. So again, here we are. The models and the data is centralized under one body, AI Inc. But now in the federated learning situation, we're changing that. The data is now outside of AI Inc., potentially on Jane, Jack, and Joe's devices, right? And we have this model, AI Inc. has it, and we want to train it on their data without bringing the data into AI Inc. So what we're going to do is we're going to take this model, we're going to pass it around, and we're going to train on each of the data points that we see while we're visiting. So we send it to Jane. She trains a little bit, sends it back. We've updated the model a little bit. Now we send it to Jack. He trains it a little bit, sends it back. Now the model's been updated again. In theory, it's improved because it's seen multiple people. And then again, we send it to Joe. And now we have our optimized model. We've trained on this training set that we never actually centralized on our machines. So how this works in practice is using a couple different technologies. TensorFlow has this kind of stuff built right in. This is called data parallel distributed training in TensorFlow. The main difference here is that in TensorFlow, usually you're working on a local network somehow, either in the cloud or on-premise. Here we want to train on potentially a network that's not local or closed. So that's where OpenMined comes in. We do federated learning through this peer-to-peer compute grid. It's a peer-to-peer network that we can send these models, these tensors around, right? TensorFlow is a library for tensor computation. So the fundamental building block of these models and this computation is a tensor. So if we can pass these tensors around and compute with them in a distributed manner, we can do federated learning in this sense. So we found out how we can train AI on data that we cannot see. We never collected that data, never centralized it, but we were able to train this AI on it. The nice thing there is that we kept the data private. We never actually saw the data, we just saw the model. Problem here is that the AI is put at risk. We sent this model to everyone. Someone could steal it potentially, which is a pretty important problem for Google. They're never going to do this stuff if that's a possibility, and not just Google. You know, any company doing AI right now.
You have like a third party that you can send data and AI model to, and then send it back.
Yes, but
guarantee the security.
Then you're just transferring the trust from AI Inc. to this third party.
Yeah, but if you have third party, you can have one party that you need to trust versus all those AI models and AI companies that you'll have to like make sure you can trust.
Was there if the party turns out to be bad?
Yeah, right.
Well,
then you just
we
like,
can make it OpenMined.
It's actually I think it's potentially worse if we're you know, right now we have 1,000 different companies training 1,000 different models. So for each of those models, we only have to trust one company. But if we centralized all those models in one company, then we really have to trust that company, right?
Yeah.
So I think
that might create even more danger.
It's not even that you have to trust the company. All those extra companies are trusting that data to that one person is also getting that model.
Yep.
We also have to trust that.
Correct. So we like this decentralization of models. We just want to potentially decentralize it even more, so that we don't have to trust single companies with all of our data. So another problem here is that the gradients that we're sending around to train this model actually do reveal information about the data. There's been research into what's called differential privacy, where you can extract data from the model or from the gradients of the model. If you have the gradient and the model, you can kind of reverse engineer the data point that was used to create that gradient. And then we've lost the privacy that we gained, essentially. And then, of course, there's the sensitive product problem. We still potentially haven't solved that. We still may not be able to train on HIPAA, like in this, we can't train this potentially in a HIPAA compliant way yet. Or, you know, a GDPR compliant way, potentially. So our new problem then is training AI on data we can't see without revealing the AI or its training updates to anyone. This is a much harder problem. How we're going to get around this, potentially, there's two ways: homomorphic encryption and multi-party computation. So the first is homomorphic encryption. I'm not going into too much detail here, but I will describe the main idea and how it works and why it's useful and when it's not. So the main idea is that we're going to encrypt the numbers that we want to compute with. You know, party A is going to encrypt theirs. Party B is going to encrypt theirs. Then we're going to swap, perform the computation on the encrypted numbers, then decrypt the result. And that result should be the same as if we would have added the two numbers together before doing any encryption. So to illustrate that, we have this 3, and we pass it through a homomorphic encryptor, and we get some cipher A. This is essentially, or for all intents and purposes, it's a randomized binary digit. So if I were to look at cipher A, I would have no idea that that was a 3 originally. So we want to do computation, so we need another number. This time it's a 5, and we do the same thing with a 5, and we create this new cipher. These two ciphers are different, but this homomorphic encryptor has a nice property where the encrypted versions, you can still perform arithmetic on that cipher, and when you decrypt it, you will still get the usual result of that arithmetic. So if I were to multiply the cipher A by 2, I would get 6, which is 3 times 2. If I were to add cipher A to cipher B, I would get 8, which is 3 plus 5. This is pretty cool, right? We can do computation. We can see the results of computation without seeing the inputs, which is the goal here. And if cipher A comes from a person's data and cipher B comes from a model, we've hidden both the data and the model, but we're still able to compute with them. We're still able to get a resulting computation, or the result of a computation, without ever seeing either of those in practice. Sure.
Does this significantly slow down computation time?
Yes, I will get to that next.
Sorry.
No worries.
Does this work essentially for any kind of math, or does it have severe limitations?
I will get to that next too.
Okay.
So first, we have there's several different kinds of homomorphic encryption, or several different categories, I guess you could say. Partially homomorphic encryption, you can only do some operations like addition or multiplication, but when you try to do something like exponentiation, for example, like a sigmoid function, you cannot do it with that way, or with partially homomorphic encryption. And there are somewhat homomorphic encryption schemes where you can do any operation, but you can only do it a few times. So we have like this idea of a privacy budget. After we do enough computations, we're no longer private. And then we have fully homomorphic encryption, where you can do an unlimited amount of any operation you want. So the problem here, obviously, PHE has constraints on the operations that we're using. Somewhat homomorphic encryption has this privacy budget, so eventually, we're going to lose the privacy guarantees. And then fully homomorphic encryption is super slow. So what follows here is an explanation of like a further deep dive into homomorphic encryption. I'm going to skip it so we can get to the demo, but if you are interested, I'd encourage you to watch Andrew Trask's talk. He goes through all this, and it was from last month.
On Epic Center?
What?
On Epic Center or where?
No, it was a different group. I'll include a link to that video and pass it around the group when we're done. So I'm going to run through these. Hopefully my computer doesn't crash.
With not too many computations for him.
Okay. Similar thing here, right? Essentially, we're doing the same thing with federated learning, but the model, the true version of the model, never leaves AI Inc. We're only passing around encrypted versions of the model and the data. So we have potentially solved the problem of revealing the AI and its training updates to people in this whole training scheme. That was with homomorphic encryption. The problems with homomorphic encryption are that it requires tons of compute, and it also requires a trusted party. Someone needs to hold the private keys for the encryption. And that's, so I mean, you could have, the model AI Inc. hold those private keys, but then they are able to access the data. So you break data privacy. You could have, so the idea there is that, at the end of when you decrypt, right, you would have a third party, kind of like some oracle, who you would incentivize to keep those encryption keys safe, so that if any data privacy violations were to happen, they would be penalized severely, so that they're going to do everything they can to protect those keys. And then, no one else has access to the keys, so no one else can decrypt the results of the computation. That's okay, it works, but it's not ideal because we still have this trusted party, and that trusted party then becomes, the target for tons and tons of attacks from adversaries, right? So,
what if you have chain of parties that will hold different sets of keys?
You could, but you're still trusting those parties. As data owners, maybe we don't want to trust anyone but ourselves. And if we can do that, that would be great, right? So in multi-party computation, we're going to try to do that. The idea here is that we're already in this distributed federated learning setting. So why don't we take advantage of that? Homomorphic encryption is agnostic to like the number of people taking part, and it works without this whole distributed training scenario. So like I can do that on my computer, you know, and it's not built specifically for multiple parties. So yeah, we're gonna dive into multi-party computation. The idea here is that hold on, let me go back. The idea here is that we're using multiple parties already, so we're gonna, in a sense, everyone's gonna have their own key, and instead of encrypting it with some like expensive encryption scheme where we can operate on the encrypted versions, we're just going to make multiple shares of the data. We're going to create those shares in a way that's unique to each party so that they and only they know how to get their share or use their share. But then at the end of that, we're going to be able to recombine it all in a way that that maintains the arithmetic like validity of the operation, essentially. So the key thing here is the share splitter, right? I'm a party. I have this value 5. This is my data. I then use this thing called a share splitter. You can look into the details of this. We can send a link to a paper or something like that. But the idea is we're going to split these shares into 5 people. We're going to do this computation with 5 different parties. Basically, I just take a random number and subtract it from that 5. So in the first case, the random number was 4. I got this 1. In the second case, it was 8, so I got a -3. The third case, it was 0, et cetera, et cetera. Then we have this other value. Maybe party 2 has this value b of 3. And they do the same thing. They take random numbers and subtract them off of that 3 and get a new series of 5 shares. We send those shares out to everyone who's going to take part in the computation. So person 1 gets the 1 and 2. Person 2 gets the -3 and -5. Person 3 gets the 5 and 8, and so on and so on. And then they're going to, we want to add up this 5 and this 3 over here. So each person is then just going to add up their share. So person 1 adds up the 1 and 2 that they got from this whole process, and they get a 3. Person 2 adds up the -3 and -5 to get a -8, etc. Then we have these shares from all 5 people now, and we recombine them. And in recombining them, we get that 8. And if you look at that, if you look at that, it's just a simple add here, right? You recombine those shares with just adding them up, and you end up with that 8. The nice thing about this is that person 1 through 5 never saw the values of A and B. They only saw their shares. Those shares are public, but the actual values themselves are kept private. And again, so go ahead.
Is this just kind of like an example or abbreviation of what's happening, or is this kind of like exactly kind of what happens?
So
you split it up and you subtract off random numbers, and then you could do arithmetic on them.
Yeah, so this is the case in addition.
Right. When
you bring in multiplication or higher order, like more complicated operations, it gets more complicated, but this idea of a share splitter and a share combiner is always the case.
So say someone hacks all the persons. They would have to know which computation gets added together. And then could they, if they were to get into everyone's data, could they get to that 8? Or am I missing something?
Each person who has a share, I believe, so the only person who has the random numbers to get all of these,
right,
that was used to generate the shares,
right,
those random numbers are all kept with the data owner.
Oh, I see. So to understand which parts get recombined.
So you would have to hack the data owner, at which point you'd have their data anyways.
Gotcha.
Yeah.
I got it.
And then the whole idea here is that like you do this in a way that if we're in a distributed scenario where
It's extremely difficult.
everyone has their own data,
Right.
it's very hard to hack everyone's data. You might be able to hack one or two people, but in that case, like, I mean, there are much higher value targets to hack, right? Especially with centralized
Right.
data.
Yeah, and all,
So-
and all the effort go into.
Yeah, right.
Interesting.
So yeah, so this is the idea behind multi-party computation. In a federated scenario, it's essentially the same thing. You get this model's public share. You basically swap shares between Jane and AI. So they have the value of the data, or Jane has the value of her data. AI Inc. has the value of the model. We swap the public shares, do the share splitting, share recombining, and we do this training by transacting over those public shares and then recombining when we need to. So now we are again able to do this without revealing the AI or its training updates, and we've kept the data private. We tried it out with homomorphic encryption, and now we moved on to multi-party computation. What's nice here is that so homomorphic encryption had a very high compute cost, but a low communication cost. The high compute cost comes from doing all of the encrypting, doing the operations on the encryption, and then decrypting, especially for more intense operations, like compute intense. So the homomorphic encryption is compute intense, but communication friendly. Multi-party computation swaps that trade-off, where MPC has lower compute cost, but it has medium to high communication cost. You have to be swapping these shares all the time and recombining. So you're moving some of the compute to communication, and which is nice because we're already in this federated scenario. So we kind of have to communicate already. So it's kind of convenient to do that. And the other nice thing about MPC is that it doesn't require a trusted party to hold those encryption keys, which again is something that we want in this is like a nice game theoretic kind of situation as far as privacy and security goes. So this is then our potential solution. We're going to train AI on data that we can't see without revealing that AI or its training gradients through a combination of federated learning, homomorphic encryption, and multi-party computation. Then we can share the ownership of that trained AI so that its usefulness is public, while the input data and the contents of the model and the output predictions are all secret, even to the owners of the AI potentially, like the AI Inc. So this is nice for the step 3 in the AI business model, where you're selling the use of the model. You can do so without potentially having to collect data in order to run the model. You can do it in a way that where the model is protected. So when you send a model out to make the inference on someone's device, you don't see the data, they don't see the model. And this also has other nice kind of like side benefits where you can host public models in a way where data privacy isn't broken potentially. And then the next thing we need though is in order to really make this a solution, I think to incentivize people to use this, there needs to be something there. People aren't just going to take control of their data privacy unless there's some incentive. So the whole idea here is then we want people to be able to transact with copies of their data within this framework. So we want to be able to price training data that we can't see with relative to other training data that we also can't see, which is kind of hard. And there's actually not been any research into this as far as I'm aware of. We're looking into it right now, actually. But we need to. Again, there's not many tools for this. We're really focused right now on building the tools, and we're going to get to this later. But we do have ideas for how this will work, and we can't see any reason why it would. So I'll talk about the whole idea of a gradient marketplace now. Sure. I don't know.
If there is a YouTube recording and some people are watching the stream, we should probably finish it first.
Oh yeah, we can break before the demo. Maybe.
Yeah, we can break before the demo. After this, and then Q&A, and then cool. Yeah. So this concept of gradient marketplace is, again, we want people to transact with their data without exposing the privacy or without being able to steal the model. And the idea here is that, this whole training happens using MPC. We're going to do the same thing with validation. We're going to validate the model against kind of a held out, test set, validation set. And we're going to use the performance to reward each participant for how much their data in particular improve the model. So you can do this a couple ways. You could have, AI Inc. could have this validation set that they know is representative of the, the distribution that they're trying to, make inferences on. And throughout training, every once in a while, they check to see how well it's doing. And based on that and who's contributed and the gradients for who's contributed, you can kind of measure how much each person's data has contributed to that particular evaluation of the model at that point in time. And if you do this throughout training, you kind of get a history of how in particular, who's contributed most to the model. So if someone's contributing random or fake data, that data is not going to contribute to the overall model performance, ideally, or at least on average.
It also enforces to share more data. The more data you share, the more it helps to train.
Well,
People encourages people to create more data.
Yeah, sure. Yeah, I mean, I think it's some. This is kind of a protection against people trying to game the system to get money for free without actually doing real data. That's how we see it. Yeah. So then there's two scenarios here. One, someone could
introduce bias when people figure out what kind of data gives them more money, and then they just
and then they reverse engineer
more and more of that data.
It's possible, yeah. And like I said, these are all active areas of research, and our goal really at the end of the day is to help that research along and get us to a point where we can use these tools in practice. But so there's another possibility here. Maybe I have a bunch of data like this that this model would find useful, and I train a generative model on that data. And now I potentially have thousands of data points that I can use, and I would get rewarded for all of those. We're kind of divided on whether that's a problem. Maybe people should be compensated for doing that, right? Maybe they shouldn't. Maybe that makes it unfair for people who can't train generative models at home. It's an interesting thought to keep in mind as we're going through this. And then another problem here is that the validation set, right, is located within AI Inc. So at the end of the day, they can kind of control who gets rewarded, and that's not ideal. So another idea we've had is that people partaking in training, you kind of randomly select a certain number of them to just be validation. They don't take part at all in model training, but they do the model validation through MPC. So then the validation, as well as the training, is distributed privately.
Compensation for crypto? You're doing computation already.
Yeah.
I know there's a bunch of is ICO really an idea?
Well, so we're not doing ICO.
Yeah, I know that.
Definitely not.
I just wondered that.
But yeah, it's right now the going theory is we're going to do fast transactions through Coinbase, not necessarily through a crypto token. In theory, we want people to bring whatever they have to trade. Like someone training a model, we want them, if they want to, pay in Ethereum, they can do that. If they want to pay in Bitcoin, they can. If they want to pay in USD, they can. Any other currency that Coinbase accepts right now. We're looking at other options for that. But that's on the roadmap. I guess I should say it's not figured out yet completely.
So the AI Inc. is like any major AI-related company, right?
Yep. Anyone who wants. Actually, it could be a data scientist. It could be an independent data scientist
who is willing to pay.
Yes.
Yeah, interestingly, I mean, there's obviously like there are like a lot of possible deviations out of it. Like, for example, on the user side, it could be another AI company that could be feeding data to make money out of the initial AI Inc., or B, feeding a lot of wrong data to like create a lot of bias in the model.
Mm-hmm.
So like
yeah,
a lot of
at that point.
but
So actually,
there could be some research done
so,
to like filter those out somehow.
Well, we do have plans around this. If the data scientist could provide a target validation score. If you don't reach that score, no one gets rewarded. Everyone goes home, and then I guess the data scientist can try again, hoping that. And you could then exclude people, right? If you can measure their performance, how well they're contributing to a model, you can have a reputation score, which Barton has actually worked on for this project. And then using that reputation score, like you could use people with higher reputation to do the validation, because the validation is kind of critical for this whole process to go through. So you could limit validation to people with higher reputation, and then incentivize people to partake in that validation. So people with higher reputation can then get paid a little more for doing validation because it's kind of like you've proven your worth. Kind of maybe it's like we need some incentive for people to want to do that and not do training. So yeah, it's basically the OpenMined in a nutshell in its current state. We'll go into, I guess, a status update and then Q&A, and then we can break and then do a demo after that. So status update, we had a January hackathon, 29 cities across the world, 400 plus were online for it, and we had 70 plus people show up in person in these different cities. We also had one in February, but that it's not on here. We have 2,400 members in Slack, 145 GitHub committers. That was as of last month, I think. Some recent milestones here: PyTorch over peer-to-peer. That is something that I worked on, which I'll be demoing. OpenMined Grid, we trained a model from the UK and Canada in 15 seconds using Keras. That happened actually, I think, earlier in the year. And some of that stuff has been repurposed, and the current state of Grid is much different than it was then. But we were able to do this. That was kind of like a proof of concept for being able to train on this peer-to-peer network. And also, we've been really interested in reinforcement learning, doing reinforcement learning in this situation. And we are working with Unity's machine learning agents team. One thing I didn't mention in this stuff is that another kind of goal of the project was to for people to be able to use not just NVIDIA graphics cards. And so we want to run on something that isn't tied to CUDA necessarily, or cuDNN. And one of the ideas was to run this in Unity, because Unity is designed to be kind of abstracted away from the hardware and to run on GPUs and all different kinds of devices, including phones, Xbox, PS4s. And like, if you look at how many people own Xboxes or PS4s, like there's a lot of people doing that, and they're asleep 90% of the time. So if those people could then use that machine to mine, essentially, in this process, that would be a lot of passive income for them, and they don't have to do a thing other than get the whole process started by uploading their data. So there are nice incentives for this, we think. And there are nice incentives on the other side too, if you see what happened with Facebook, or there's, and with GDPR coming in right about now, and the potential for other similar laws to show up in other countries. I think that it's a really good time to be working on this stuff and to be making it possible to do private machine learning. Roadmap. We want to do federated learning with PyTorch. That's kind of like a first step. We've decided that PyTorch is nice for this use case. There are also people working in TensorFlow on that angle. In particular, Morten Dahl, who's a cryptographer in France. There's a really good blog post where he showed how you can use machinery already in TensorFlow to do multi-party computation. it wasn't over a peer-to-peer network, but still extremely valuable. And it's interesting. It's going to be interesting to see like what comes out of that work. And then next thing we want to do after we have federated learning is to include MPC training. My friend from Cleveland, Bobby Wagner, is working on an MPC like toolkit for PyTorch, but he's also making it so that it's kind of agnostic to what's underneath it. That's the goal. And that's like currently in progress. We work on that quite a bit. And then rapid grid payment via Coinbase. We already had like a prototype for this, but it needs to be adapted heavily to like our current setup. And there's going to be a lot of breaking changes in the future too. So like all of this is moving very quickly, and that's why this is later on in the roadmap. And eventually we want this stuff to be application ready. We want people to be able to use this to train models and then either host those models and do, private prediction, either with our tools or with other tools that other people are working on. Hopefully we can use something like Onyx, the Open Neural Network Exchange, to migrate models from system to system and hopefully create like an ecosystem where you can do your training here and then do your hosting and prediction over here and have everything production ready long term. So that's the long term roadmap. There's a long way to go, but if there are questions, I feel like we took Q&A throughout, which is nice. I think that was a really good way to do it. But, cool.
I was wondering, how can you like work on the model with the output?
Hit him from who?
What you said earlier was so like with the splitter to send them the data and like you said like hey, the AI company like be able to see
The outputs.
the outputs. So like how would you be able to like work on the AI itself? Are you just going off like results, like seeing if it works right as it is, or?
So in most of these setups, someone can see the output. Yeah, I don't think right now there's no research that I know of that I've heard of that prevents like privacy loss through prediction, I guess you could say. And yeah, I mean, in theory, right? If you didn't have access to the outputs, but you could still compute on them, you could get evaluation metrics for the model in aggregate, and there you wouldn't have privacy loss, but you'd still be able to track the progress of your model. Because if somebody has access to the data, and you're in this multi-party scenario, you can use MPC to compute with those numbers in a private way, and then someone can get the result. And if you set it up right, the evaluation metric could be sent to the model owner. That's kind of like how I think we would do it. Yeah.
That's a great question. Do you ever have a problem with the variability of upload and download speeds from all the different people doing computation?
Yes.
Like one person holding up the whole thing?
Yes, absolutely. We have a few ideas on how to handle it. I mean, this stuff isn't like scaled yet, so
No, yeah. It's an interesting, tricky problem.
Yeah,
Right? It could be just like a little thing, and then all of a sudden they start working fine. And like,
Right.
You just do it drop out. Like if it doesn't respond,
Right.
it doesn't out.
Oh yeah,
And then you're like,
yeah, that's the idea.
system's
Yeah.
or something.
like a health
Right.
check, right?
Yeah.
So basically, if the person is taking too long, just drop him.
And also the nice thing about having like a reputation system is that you can make that reputation represent whatever you want. That could include something like reliable internet or reliable computation
So
speed.
what does SETI do? I guess would be the question.
What?
What does SETI do? I guess would be the question.
SETI? Yeah. There's a lot of other projects that we can draw on their information. Yeah. We're not the first people to be doing like large scale distributed computation. Yeah. So, which is nice. I mean, we're using IPFS under the hood, which I'll get into in the demo, and that was built to be kind of like scalable and resilient, ideally. Which is it's the IPFS is the interplanetary file system. It's a file system that's peer-to-peer with kind of like lazy uploading and downloading and stuff. And it's based on, I think it's used in like the Ethereum circles, like their development and stuff. the people who put it out, Protocol Labs, they deal with a lot of those. They build tools for kind of decentralized technologies or whatever, and so yeah, we've kind of been piggybacking on their work a lot, and we've been kind of pushing the boundaries of what those protocols can do, I think, and we will continue to, I'd imagine.
So, in terms of the part where you're evaluating the marginal value of a data set, right? So if a bunch of people have already come up with a bunch of data that trains it to a specific point, right? You don't want to be more people to do that. Could you just make more of the same data? Could you take two different data sets and determine whether they actually cover a different part of the space for modeling by combining the data sets and seeing how the model performs with combined data?
Yeah.
Is that an avenue of research that's currently active?
I'm not sure if it's active. I don't know if it's out there. So just like spitballing, one thing I could think of is you kind of like, you could try to learn the distribution that each of the data sets comes from and then measure the like difference in that distribution with something like KL divergence or something like that, which is like it essentially just measures the distance between two distributions, like from an information theoretic perspective. So there, yeah.
This thing more in terms of if you actually train the model on a combined data set, I guess I'm sort of thinking about this the way that you might think about a Kalman filter, wherein you have you have a measurement and you have a prediction, and both of them are distributions. And if they are different, the more different they are, the more you learn from the second distribution. Therefore, if you were to take two data sets and combine them, then if they are marginally valuable over each other, then the performance of the model should be better in the combination than on either of them.
Yeah, I think that's just a general like property of machine learning models, or some machine learning models, I guess. Like deep networks are known to scale well with larger volumes of data, performance-wise, but things like district regression or random forest kind of peak out earlier. So
also the privacy could be a problem, right? Because then you having to combine data sets that you already are trying to separate.
Yeah, but the problem is, yeah, obviously you have to deal with the privacy, but sometimes you may reach certain peak of the model on a combined set, but not iteratively if you just feed the data once at a time, right? So it's good. Any upcoming hackathons that you're aware of?
Not that I'm aware of. I think we probably should start one. I think
That's
it's
a good
time.
idea.
We have a lot of work right now. It's kind of tricky because the NIPS deadline is coming up, the Neural Information Processing Systems Conference. Deadline, I think, is in like a week or so. So some of the contributors have been working on that and not on the project right now. But after that deadline, I think there will be a flurry of activity on all of these different projects. Right now, like there's a lot to do, and we'll see how it goes. So if anyone's interested in contributing, there's join the Slack. There's we'll send out some links that will get you right where you need to be. So
how long has this project been active?
So it started last July, I believe. It was like when it was announced and stuff, and then there's been a lot of progress very quickly, and but this being kind of like on the forefront of current privacy research, a lot of things are unknown. So mistakes are made in strategy and stuff, which aren't necessarily like, not many people can prevent that. You know, like new research is coming out that's saying, you know, this approach that we had is now invalid, or, you know, we need to go rethink this. So there's been a lot of refactoring, re-strategizing, things like that. But so yeah, it's been going on since July. It picked up quite a bit in the winter to get us to where we are now, I'd say. But
Yeah, it's a good point to break for.
Yeah, let's break. We'll come back with a demo after.
Good job, man. I think it's like still a great project for the
No, I'm going places.
Sorry? You mean the Jupyter Lab, or? I think that's a regular Jupyter, but I have used Jupyter Lab. It's pretty cool. I like it a lot. So. That pizza that smells delicious.
Mm-hmm.
All right. Yeah, just like. All right, guys, we're kicking it off. So Jason will be showing the distributed model training on OpenGrid. Yes, if it was by OpenGrid is.
Yep. Okay. So OpenGrid is like the kind of the guts of what's going on here. So it's the infrastructure that's going to allow all this stuff to happen. The project right now is split into multiple repositories. We have multiple tools here going on. And the goal is to run these private machine learning models at scale on a peer-to-peer network so that anybody can join and transact their data. So we need, in order for that to happen, we need infrastructure to do all this on, a peer-to-peer network. We're using IPFS for that. But OpenGrid is kind of like the platform that we've created to facilitate all of that. We have PySift, which is a Python API to private machine learning tools. It will include implementations for different private machine learning techniques, and it should be able to interface with Grid in the distributed setting. And then there will be, also contained in OpenGrid, there will be the machinery around rewarding people for their data, and the whole transactions piece should be there. So right now, OpenGrid just has the infrastructure. It's running IPFS. You're able to send objects over IPFS, send files. Kind of an introduction to how IPFS works is a little bit beyond the scope, but what I've been working on for OpenMined for a while now is integrating Torch into this IPFS platform that we've built. So that's what I'm going to demo now, and hopefully everything works. So to start, we just like import all the stuff like we normally would with Torch. You know, we're going to get Torch, the main library that has all the tensor computations on it. Torch NN, which has like some neural network specific stuff. Variable, which is kind of Torch's object for AutoGrad, which is automatic differentiation, which is very useful for deep learning in particular, for gradient-based machine learning in general. And then we import our Torch client, which is kind of the interface between Torch and OpenGrid. And that's what we're going to use primarily to hook into Torch and to allow it to communicate with other computers over this network. And then we're, just NumPy and regex for some help. So right now it's connecting to IPFS. It has this ID right here, this client ID. That's the ID of my computer. and then it just finds kind of my OpenMined folder on my machine. It connects to some known workers. This is just to bootstrap kind of the connection process. And then it, searching for nodes, it found 28 nodes on IPFS and one that's specific to OpenMined. That's the one that I've prepared for this talk. And then once it's done with that, it hooks into Torch. And what it's actually doing is overloading Torch functions and methods with alternate versions that we've created to allow for interfacing. What's actually nice about this is that it's doing this completely generally. We didn't have to go and rewrite every single function in Torch, because there's like over 1,000 of those. I wrote maybe like 3 or 4 specific methods for sending, getting, and also some stuff to handle like new variable creation and stuff like that. But all the general Torch methods like Torch add, matrix multiply, clamp, minimize, maximize, all that was done automatically with like a single function and just looping over those with that function. And then that's how this works. We can see who's on the network right now. We have this anchor. That's the anchor that's like bootstrapping the connection process for anyone who joins. And then this compute node, that's a computer that's actually available for computation. It has my email address because that's who started it. And then it gives some information about the machine. I have 8 CPUs available, disk utilization and memory utilization. And if there were GPUs on this machine, they would show up here. So that I would know, kind of the order of magnitude I can expect from like a computation perspective. So this is just gathering the compute nodes from the network. If we had more than one compute node on here, it would show up there. This was a debugging line. I'm not going to matter there. So I'm just pulling out the compute node. And what I'm going to do is send a tensor over to this node, square it, multiply it with itself, and then get the result. And this is the result. We have this matrix 1, 1, 2, 2. When we square it, it becomes 1, 1, 4, 4. That was done over IPFS. We sent the tensor, did the computation, and received the tensor and pulled it back. So we can do this with you can substitute any normal Torch operation that takes in tensors and outputs tensors here. So you can do essentially very general computation in this framework in a distributed manner. This computation was done remotely. It was not done on the client process here. Yeah, so you're in control of all of the. You're in control of all of it. When you create a tensor, you send it somewhere, and then you can do as much computation using that tensor that you've sent, and the result of the computation will be stored on that machine until you retrieve it. That's what this line here, y.get does. And then, like if I were to print out, I'll actually show you later on. We'll break it down here. But we're going to move beyond tensors and talk about variables because that's the major object in Torch that deals with differentiation, which is kind of critical for this to actually work in practice. So all of that stuff can be found in the torch.autograd package. And actually, like a small note about this is that a couple days ago, I think, they came out with a new version of PyTorch where they merged the tensor API and the variable API. So some of this code is now deprecated. It still works, but they're moving to a new API. So we will eventually update, but like I said, it takes time. So again, we're going to do a similar thing. We create 2 tensors. They're the same tensors that I created above, x and y, just to print out what x looks like. It's a normal variable here. Oh yeah, we wrapped in a variable that requires grad equals true. That allows us to do differentiation once we compute with these objects. But just some information here. It looks normal, right? These are some grid-specific attributes. You have owners. Right now, the client owns it, which is me. It has this ID, which is how we're going to keep track of all these different objects across the grid. And we have an attribute for is pointer, which is just a nice helper that says, is this on my machine or is it somewhere else? Right now, it's false because the variable is on my machine. So now we're going to send it to another machine. Then we print out the same information, right? Now we no longer have that data. It just tells us the location of the tensor, or the variable, rather. It's now on this compute node instead of a client node. Then these grid-specific attributes, they've changed. The owners is now different. The ID is the same, right? Because we want to keep track of it no matter where it is. But now it is a pointer object. It does not contain the data. It only contains kind of a wrapper or a pointer to it. So this variable, or x and y, both are not on my machine, but I'm going to compute with them anyways. So I just did a matrix multiplication of x times y, or x matrix multiply y. And then I got this z object back. This, again, is a pointer to a variable that's on a different machine. But it has a different ID because it's not the same as that x tensor anymore, or that x variable. It's now the result of computing x with y. And we still have access to it, but the data's not here. So why is this cool? One, we didn't have to change our torch code. This is exactly how you would do this normally in regular PyTorch. But the actual computation was performed elsewhere. I also didn't cherry pick this example. I didn't just choose matrix multiply because we'd implemented that already. We've implemented, like I said, all of these methods in a general way so that you can, do any computation here, and you can do any chain of computations there as well. So you can chain them together because we're actually getting a PyTorch variable as the result of it, even though the data is not local.
So it just auto
yeah, so I guess what's happening under the hood here is we have a variable. We have two variables. We sent them somewhere else.
Yes.
We matrix multiplied them together using the pointers. But it knew that instead of actually multiplying these empty pointers, it needed to send that command to that other machine, perform the computation. Now it has the result over there with the data and everything. And then it sent a pointer back for us to reconstruct a pointer to the new object. Now, yes. So the idea here is that, so the result is on that machine, but I have a pointer to it, which means I can use the result of that computation in future computations without actually returning the data to my machine and doing anything. So you can chain together operations like this, which we'll do in the future. So another thing is that we can now, because we're using variables, we can do derivatives on these computation graphs. So I'm just going to sum up the results, the data in that pointer object, and then I'm going to call backward on it like I normally would if I was going to take the derivative with respect to the inputs. So I just did that. It executed. But now I want to see the gradients of that derivative with respect to x and y. So I'm going to return x and y to my machine. There they are. Or no, actually, no, those are the gradients of x and y. So what we've done is all that computation we did over there, we were able to do the derivative of that computation and then return the gradients to my machine so that I can use that information locally. This is really important for federated learning because we're not passing around data. We want to just pass around the gradients. Right now, I actually needed to pull the data back in order to get the gradients. But in this case, this is still okay for federated learning because we're only going to be sending the weights of the model around. We're actually not going to, like if the data is already there, we don't need to retrieve the data ever in order to continue training the model. We just need to pull back the weights of the model and then do things with the gradients attached to those weights. So I'm going to go through that now. So there's some, caveats here. We haven't scaled this really. So, and there are limitations to how much data can be transferred in IPFS. Right now, the max block size is 1 megabyte. And that's not really viable for larger models. For example, if you're training an embedding matrix, that could be, you know, a lot more than 1 megabyte. It could be 20 megabytes or something. Yeah. Yeah, so if you commit something to IPFS, you're in, unless you do some extra stuff, you're only committing that blob or whatever. That it gets packaged into a block and committed to IPFS. And it will, if it's over 1 megabyte, it will just truncate, yeah, if it can. So they've implemented sharding, but we are not taking advantage of that yet. We need to, and there's an open issue about it. But yeah, so you know, the kind of the standard is MNIST. I'm not going to use MNIST because the weights in the first layer of an MNIST network would usually be too large for this. So I'm going to use the Boston housing data set. Until we implement that sharding, we're kind of constrained with what we can do. But that's what I'm using. So just loading the data, turning it into torch tensors, pre-processing, basically just standardizing features, except for this one because it's a binary feature, so there's no reason to. And then that's that. Did I run that? Yeah. Establishing hyperparameters. These are fairly common. Keeping the batch size low, just so that it all works smoothly. I haven't tested with higher batch sizes. It probably would work because we're not even close to that 1 megabyte here. Learning rate, epochs, and then we have this update master every. That's the frequency that we're going to broadcast the new model to the workers. Here we're doing it every 3. We could do it every 5, every 10. We could do it, you know, every single one. That would just be kind of like normal training at that point. And it would increase communication costs. So a lot of times you do this every once in a while, and it still will learn well, and you won't be wasting time on communication. This is all kind of following the parameter server way of doing distributed training that was kind of popularized by TensorFlow and Google with their work. So anyways, we set up the architecture. We have kind of the input shape. This is just the shape of the first layer. First layer, neurons. We're going to go with something small because we have a pretty simple data set here. Second layer. And then this is just getting the number of output neurons. You know, if we were doing multivariate regression, we'd potentially have multiple neurons that we're predicting. But here, there's only one dependent variable, so it'll catch that. And then we're going to start pulling in the PyTorch stuff that's specific. So they have some nice convenient wrappers and objects for this. Tensor data set and data loader. Or just data sets and data loaders. These are pretty common to use with PyTorch, but it's a little bit beyond the scope here. So now that we have this, essentially we're going to use this data loader to get new batches that we can send to workers. Because, you know, in theory, the data is going to live on the machines already. Here we don't have machines with data already, so we're just going to create the data and send it and train with that data as if it were private data, or just distribute data that was already distributed. So that's just doing that here. As you can see, it doesn't take too long, which is nice. IPFS is very fast, and actually, the sending is lazy. So this is all happening kind of lazily. So it's sending, but it doesn't actually download it from IPFS until the other machine needs to use it. In this case, the code, I think, is set up so that it will unpack it right away. But that's just a nice property of IPFS that we'll definitely be taking advantage of in the future. So yeah, so now that we have this collection of pointers now, because we've sent them, so the data is no longer here, but we still have the pointer objects, which are in batches of features. These are 2D tensors, right, with batch size and number of features. And now we basically have everything we need to set up the network and train with it. So this is just setting up the parameters. I'm doing this without any actual layers because we still haven't exposed all of the new methods that we've introduced to those higher level like neural network layers. So we're going to do this like the old-fashioned way with like base NumPy almost, except we're going to use PyTorch so that we can communicate over grid. And this is kind of standard initialization, right? We're going to use Xavier initialization depending on the activation of the layer that follows. And then, yeah, that's all fairly straightforward if you look at it later. And I'll upload this. This will all be available later. Some helper functions, because we don't have those neural network layers that come with PyTorch yet. This is just a ReLU, a linear transformation, and mean squared error, because we're doing regression. And then we need some helpers for actually updating the model. And these are kind of different than the normal ones because, we need to average gradients. Normally, you don't need to average gradients over like from different machines, but because we have gradients coming in from different machines, we want to average them in order to update the model. And then we have this update params that actually does a single update step to using just standard gradient descent. You could get more complicated with this, add in momentum, use atom, something like that. But for now, we're just using, for illustrative purposes, kind of like the normal stuff. And then there's reset flags, has to do with some quirks around how AutoGrad works. In particular, I'm going to be substituting the weights in place with new versions of themselves. And that's kind of a no-no in terms of PyTorch. So there's a few extra things you have to set because of that. But anyways, this is the main training loop. I'm going to kind of explain it before we go through it all. Delete that. Anyways, these are just helper lists that we're going to use to assemble the gradients. We're going to hold on to those until we, until we are ready to update the model, and we need some place to store them. It's kind of like a buffer for the gradients as they come in. We're going to loop over epochs. Right now, I think it's set to 5, just so we don't sit here all day. And then we're going to loop over these batches, but they're distributed batches. They've already been allocated to the workers. So the first thing we do is we broadcast the current weights, which we created originally up here as parameters. But we're going to want to do that every so often anyways, because we need to, as the weights get updated, we want to send them out to the workers so they have the most current version of the model. Then we are going to pull those clones, I guess. We clone the weights so that we maintain like a master copy of the weights. And we're going to clone them, send them out to the workers. And then we need to pull those clones out so that we can operate on the clones that are distributed. Basically, we want to operate on the stuff that's out there, not the master weights that we have here. Anyways, once we have those, we're going to use those in computation. This is a forward pass through the network. You take the input, xi, do a linear transform in a ReLU. That's the first layer pass. We get the first activation. We do that again because it's a multi-layer network. Get the second activation. And then here's the output. We're going to do a linear transformation of that with the final weights. And because this is regression, we just aren't going to use any activation function. It's just going to be like a normal linear unit. And that's going to be our prediction, y hat. And that's just so that the shapes match up for what we're about to do. Here we need to make sure that we have type safety. So we're going to take the actual label, yi, and make sure that it has the same type. That is, that they're both floats instead of doubles. And then we compute the mean squared error. That's the loss function. We compute the derivative of the loss with respect to the weights. This actually does, technically it does the derivative with respect to any leaf nodes in the computation graph, but the ones that we care about are the weights of the neural network, and we'll be able to do that. Once we've done that derivative, we want to return those parameters from the workers. And then we want to pull the gradient from each of them and add them to that kind of parameter storage buffer. It's like that storage that we set up originally to hold all the different gradients from all the different workers. And then every so often, we're going to update the master parameters. How we do that is we take those gradients that we've stored, we average them together to get a final gradient that we're going to use to update the weight of the model. This is essentially how the parameter server scenario works in TensorFlow. It's just doing it over a peer-to-peer network instead of doing it on a closed network. And it's doing it with PyTorch instead of TensorFlow. And then, like I said, we've kind of cheated PyTorch a little bit, so we need to reset some stuff for the weights because we've updated them in place here. And then we no longer need the gradients that we've collected, so we clear them out just by replacing that with an empty list. And that was a debugging thing. So I'm going to run this now, and hopefully it works. So it should print out when the epoch is done, or it'll print out an error. There we go. That hits the first epoch, and it'll continue to do all 5 like we programmed it to. Yep. Yeah. So, yeah, we have people working on TensorFlow. Actually, the original stuff that was done with this, like the model that we trained from UK to Canada, that was using Keras. It was basically just doing an update step in Keras, saving the weights, sending it over, receiving it, downloading it, doing more training, sending it back. Kind of. That was how it was done originally, and but now we've realized that that's kind of limiting. We can't do all the things we want to in that, or at least it's fairly difficult with Keras in particular, which is why we've gone on to the lower level libraries. Like PyTorch has a lower level library like this. That's been useful. TensorFlow has obviously theirs. It's a little bit harder, I think, with the compile and run versus like the dynamic frameworks. PyTorch does dynamic computation graphs, and TensorFlow does static, which I think makes it tricky. But so I mean, like I said, Morton was able to get MPC running on like a TensorFlow using TensorFlow distributed, and which is cool. I think there's some bugs to iron out, like it doesn't always send shares where you'd want it to and stuff. But no. Right now it's all Python. Yeah, so there's actually someone was working on a JavaScript library, I think. What? Yeah. I mean, well, so there's this. I think it's in response to there's this interesting idea coming from a lot of people where maybe we want to train models in browsers. Like if you can mine cryptos in browsers, why can't you train a model in theory? And you can do federated learning that way potentially, because everyone has a browser. It's kind of the idea, but yeah, I mean that's still kind of new, early days with all of that. Yeah, I mean, I think ideally we want to have as many APIs as possible. Right now we're focusing on Python because that's become like the dominant language of choice for machine learning engineers and researchers. It seems like. So, but I mean, in theory, right? We're training with PyTorch, so we have access to anything that Onyx, the Open Neural Network Exchange, can access. That means we can export these models that we've trained to, Cafe 2 or whatever, how do you say it? MXNet, basically any deep learning framework that's part of that, you can export there, and they have kind of production-ready systems that are written in C++ or C or Python or whatever else they have. So I mean, we're kind of banking on Onyx growing in terms of size and complexity, and also if we get this running on TensorFlow has APIs in all kinds of stuff. They have JS, they have Swift, they have Go. I think they have R. Well, I think that's through That's through Reticulate, and that's kind of a weird solution, I think. But yeah, and Keras are, yeah. Well, I mean, a lot of times you wouldn't want to use Python because it's slow. Well, then you definitely would not want to use it in R because it's translating R into Python into C++ and then coming all the way back up. But yeah, that's the demo. If there are any questions on how this works, of course, I'm available. And yeah, I obviously, like, this is still very new, early days as far as like how this is working and stuff. There's a lot of debugging that needs to happen, and it's pretty hard to debug when you're working on a peer-to-peer network. But we have a lot of good plans, and we have a roadmap set up so that once this is all a little bit cleaner, the code base is a little cleaner, like everyone can contribute asynchronously and all that stuff. So, yep. Can you explain one more time?
So,
Mhm.
one of them is where you like, oh, I only want this data to reside in a certain set.
Mhm.
That's it.
Mhm.
And the second part was these IPFS sort of what's the motivation for some of the IPFS storage? For example, for this really high
Mhm.
so
So the incentive to run, all right, I guess I'll start with the easy one, which is can you choose who to send data to over IPFS? Yeah, absolutely. We got a list of all the workers that were on the network, and you're free to manipulate that list as much as you want. It even has names and email addresses. User input. But. I'm actually not sure how that works necessarily. I think I've from the conversations I remember having, IPFS is lazy. So if you commit, it stays on your machine until someone else needs it. At which point it pulls it and downloads a copy. Yeah. So unless you specifically requested a piece of data, that wouldn't be possible. And in our framework, that's not possible to do. There's no way for a worker to access stuff on the client that the client hasn't expressly sent to them. Yeah. So right now, there's a design choice we had to make about whether we wanted to make workers and clients symmetric or not. We chose asymmetric for that and for computational reasons. But yeah. So the second question was, how do you incentivize people to set up these nodes? The idea then is right now there's no incentive. There's nobody on the network actually, unless we're developing. So again, the last piece is the gradient marketplace, where you're actually incentivized financially to join this network and to host your data privately. Because without the privacy, it's hard to make people get there, and without the money, it's also hard to get people there. So even still, with both of those things, it's going to be hard to get people there. But I think there are other ways of getting data on this than having individual consumers bring their data to it. I think you could work with companies that already have centralized repositories. I mean, think about if hospitals could transact on other hospitals' data privately and reward each other for doing so. I think that's a nice use case for this. It goes kind of beyond the individual consumer level. But ideally, we want individual consumers being compensated, regardless of where the data is being stored. If it's their data, we want them compensated for it. So it's going to be interesting to see how we get there.
You have V8 in mind?
Of that?
Yeah, how long do you need?
Yeah, that's not going to, you know, our roadmap is to get these tools in place. We want to get those in place as soon as possible, but and we want them. The way we kind of see it is like, or the way I see it at least. I shouldn't speak for everyone, but I think these tools being in place is necessary for that paradigm shift to take place, but it's not sufficient, and there will need to be other changes from either within industry or within like regulation, lawmakers and stuff like that. And we already see that kind of with GDPR happening, and there have been there's been some early talk of other countries doing it. I think China may have introduced a bill that's similar, maybe smaller in scope, but has similar implications. And I know that, I mean, it seems like the conversation is shifting in the U.S., but I think that might just be the stuff that I read and maybe not the general populace. But we'll see. I mean, no, I think that's a question that's kind of open. What? In the U.S., yeah, I agree. Yeah, I mean, you know, it might be hard to pass GDPR in the U.S., right? But maybe a different version of it that will get us closer might be feasible with bipartisan support. So who knows? That's a whole conversation. Yeah. Well, let's yeah. I don't know. We'll see. We'll see about all that. Who knows? Who knows what could happen there? Like. Yeah. We'll see. We'll see how it goes.
Well, thank you, Jason, and also I want to thank Comcast for hosting us and making it possible, and also for providing the pizza.
Yeah, thank you. Absolutely.